Area of a region between two curves. If you look at figure 7.1, we are going to try to find the area between two curves, F and G, between two distinct x values, A and B. In Calculus 1, you would integrate to find the area under one curve to the x-axis. But the moment you bring in a second function, you'll need to find the area between them in some cases. Let me scroll. Figure 7.2. The reason that this subtraction and formula works out is when you integrate only f, this is the middle figure, when you only integrate f, you're finding all the area between the x-axis and function f. When you integrate only g, you're finding the area under g and between it and the x-axis. So by subtracting, you're taking this total area and removing the area outside of the intersection zone, giving you the area between the two curves. And so this will be our formula. We're going to integrate from A to B. Those are the distinct x values. The top function minus the bottom function. If f and g are continuous on a closed interval AB and function g is less than or equal to function f for all x in the interval, then the area of the region bounded by the graphs of f and g are the vertical lines A and B, so your area is calculated as the integral from A to B, top function minus bottom function with respect to x. Let's look at some examples. In this first example, we're asked to write a definite integral that represents the area of the region. Our first function given is the parabola x squared minus 4x. The second function is 0. That's just the x-axis itself. Let's go to the picture at the right of your screen. X squared minus 4x is this parabola. The x-axis, which is y equals 0, is this horizontal line. The area that we're after, the x-axis, is actually on top and the parabola is on bottom. So we have to be careful. We're going to integrate from 0 to 4 because that's the distinct values of x that cut off our area. But we need to make sure that we have top function minus bottom function. Distribute your negative sign, that's 4x minus x squared. Take the antiderivative, integrate, so 4x becomes 2x squared, x squared becomes x cubed over 3. Using second fundamental theorem of calculus, we're going to plug a 4 in to this expression, and then we're going to plug a 0 in after we subtract. So plugging in a 4, that's 32 minus 64 thirds. When we sub 0 in, that just goes to 0. This calculates to 32 thirds, and that's the area of this beige area between those two functions. Let's go. Write a definite integral that represents the area of the following region. We have two functions. One of them is x squared, the other is x to the 5th. We're only going to investigate from 0 to 1. Why? If you come over here to the figure to the right of your screen, these two functions intersect at 0, 0 and 1, 1. X squared is the function that's on top during this interval, and y equals x to the 5th, which is your second function, it's the function on bottom throughout the interval. We're going to integrate from 0 to 1. Those are the distinct x values, 0 to 1. We need to make sure that our top function goes first. So x squared, that's the parabola on top. X to the 5th is the function on bottom. Top minus bottom. Integrate x cubed over 3 minus x to the 6th over 6. Don't forget to sub in 1 and 0. When we sub in 1, we get a third minus 1/6. Plugging in 0, we get zeros. This equals 1/6. That's the area of this blue region. For this one, we have x values given, and basically it helps bail us out on finding the intersection points, to be honest with you. So we have x squared plus 2. That's a parabola. Crosses the y-axis at 2. Looks just like x squared otherwise. The second function is negative x. And that's a line that goes through the origin with a slope of negative 1. These two actually don't intersect at all, but we're still asked to find the area between x equals 0 and x equals 1. So if you look at your diagram to the right, let me try to blow this up a little bit. There we go. From 0 to 1, it's just this little bitty blue section in here. So we're going to try to find the area of that shaded region. X squared plus 2 is the function on top. Negative x is the function on bottom. So we're going to integrate from 0 to 1. Top function minus bottom function. X squared plus 2 minus negative x. That's plus x. Rearranging your terms, we have x squared plus x plus 2. Take the antiderivative or integrate. X cubed over 3 plus x squared over 2 plus 2x. Evaluated at 1 minus evaluated at 0. Luckily 0 just gives us all zeros. So with x replaced with 1s, we get a total of 17/6. And that's the approximate or the exact area for that shaded region. Find the area of the region bounded by the graphs of f of x equals 2 minus x squared and g equals x. 2 minus x squared, that's a downward opening parabola crossing the y-axis at 2, opening down like negative x squared. G of x equals x, that's a line that passes through the origin with a slope of positive 1. These two functions intersect when x is negative 2 and 1. If you set these two functions equal, solving for x, you'll get negative 2 and 1. We're going to integrate from negative 2 to 1. That's the left x to the right x. Integrate from negative 2 to 1. In this particular diagram, our parabola is on top, our line is on bottom. 2 minus x squared minus x. Rearranging terms, let's integrate negative x cubed over 3 minus x squared over 2 plus 2x. Subbing in a 1, you'll find that in this first bracket, minus. Subbing in negative 2, you'll find that in the second bracket. Doing our calculation, the first bracket gives us 7/6, and I was kind of too lazy to calculate the rest of that second bracket, but carefully put this in your calculator, and you should find 9/2 as your total area of this blue shaded region. Find the area of the region bounded by the graphs of sine and cosine. I color-coded our graphs to the right of your screen. Sine is the black ink graph. Cosine is the red inked graph. If you remember from your unit circle, cosine is the x-coordinate at any angle. Sine is the y-coordinate at any angle. These graphs intersect in multiple areas. We're only going to look at this shaded region here. As you go around your unit circle, at pi over 4, sine and cosine are both square root of 2 over 2, meaning they're equal. That's our lower bound. As you work your way around the unit circle, when you get to quad 3, at 5 pi over 4, sine and cosine are both negative square root of 2 over 2, meaning that they're equal. So these two functions are equal in one trip at pi over 4 and 5 pi over 4. So those are our integral limits. The graph of sine is above the graph of cosine during this interval. So I'm going to do sine x minus the bottom function cosine x. Integrate. The integral of sine x is negative cosine x. Integrating negative cosine x, we get negative sine x. Evaluated at 5 pi over 4 minus evaluated at pi over 4. So first time through, I plug in 5 pi over 4 for my angles, minus, and then the second time through, I plug in pi over 4 for my angles. These are the values from the unit circle, and if you carefully calculate, you will get 2 square root of 2 as the area of this blue shaded region.